I did not feel very, I felt like I was gonna vomit, and again, it took me 30 minutes to finish one problem, and then I only had and then another problem took me 15, and then I had the rest of the remaining time to finish like 6 or
oh wow,
problems.
it's a lot of problems.
And it's just like, yeah, it's not great.
Is he, I forget, he usually gives like a practice midterm, right?
Mm-hmm.
One thing, thinking back, I'm surprised I haven't said this in the past, but one thing that I found helpful when I was a student was actually taking the practice test like an exam.
Yeah.
So sitting down, giving myself 50 minutes, no notes, no, only the stuff I'm allowed to have, and then trying to practice working efficiently. Because certainly that's part of taking an exam is managing your time well.
I'm just not good at it. I'm trying to get some accommodations, but like they're like, you get temporary accommodations, but how?
Yeah.
Because it doesn't seem like it's possible to get temporary accommodations without like a therapist, and I can't do that when I don't have a therapist.
Right.
I'm currently going through Medi-Cal, issue with Medi-Cal.
Yeah, that's I don't know. I feel like I understand what they're getting at, but they do make it really challenging for students to get that. Like you have to have so much documentation, et cetera, and yeah, I don't know what to say about that other than it's less than ideal. Start this. Have I started the Zoom? Yeah, I started the Zoom. I have a final review we can go over. Although if there are things either of you want to look at, we certainly can. I was going to probably review if that sounds good. We can jump around or we can just kind of go straight through it. Excuse me. Also, there are solutions posted to this on campus, so I don't imagine we would actually get through all of it, but if you want to.
Is this your final review?
Yeah, this is the one that's posted on campus.
Okay.
I didn't see any practice final or final review from Dr. Goodell posted on his campus yet.
Mhm.
So
you made one.
Yeah.
Okay.
So let's start with problem 1. And if you guys feel like you want to jump around and do something else, we certainly can.
I feel like this.
Okay. So here we got the function. Let's sneeze. Oh, thank you. All right. So we've got a function of 2 variables. It is x squared plus y squared minus 2x plus 4. And first and foremost, we want to find and classify the relative extrema. So finding them amounts to setting the partials equal to 0. So we're going to find fx, which is 2x minus 2, set that equal to 0. And we're going to get x equal to 1. Fy is 2y, set that equal to 0. We're going to get y equal to 0. So we're going to get one critical point here, which is 1, 0. And then we're going to test it. So we're going to calculate d, which is fxx, fyy, minus fxy squared. Fxx is 2, fyy is also 2, and fxy is 0. Not very exciting, right? A lot of times when you find this d thing, you actually have a place to plug in your critical point, but there's no x or y to plug in for. So we just get a d with a value of 4, which is positive. So when d is positive, it means we have a max or a min, but not a saddle. Whereas if d is negative, we get a saddle. So then the test to see if it's a max or a min, we look at one of the second derivatives. So fxx being 2, which is positive, means that F is concave up. So we have a minimum, a relative minimum at our critical point. Let's look at part B. Yeah, we probably need to finish that. Let's try to. Part B, we want to. Also, please stop me if you have questions. We want to find the absolute extrema of the same function over the triangular region bounded by the points -1, 1, 2, 2, and 2, -1. I always find it helpful to draw this kind of thing. So absolute extrema. Oh, sorry. This have a relative minimum. We'll draw the triangular region. I'm just going to draw the corners, vertices, whatever you want to call them. So let's see, so -1, -1. There, 2, 2. Oops, that's not -1, -1. It's -1, 1. Oh well, I don't want that one. Excuse me. So -1, -1. I want 2, 2. And I want 2, -1. Not that it has to be, but typically if your region is triangular, it's going to be a right triangle. Doesn't have to be, but often it will be just because it's easier for us to find the equations. So we have the point 2, 2, 2, 1. And we have some walls. This wall is the wall x equal to 2. This is y equal to -1, and this is the line y equal to x. So we're going to test the following points. We're going to look at f of our critical point, which was 1, 0. We're going to look at each corner of the triangle. And then we also have to find the critical points along each wall. That's always like the extra part for this kind of problem. So looking at the walls, let's look at y equal to -1 first. I should write down my function again, just so we know it. F of xy is x squared. Oh wow. You might have noticed I wrote down the wrong function when we started. You might not have noticed. I wrote down x squared plus y squared, and the actual function was x squared minus y squared. We can still do the work for this function, but just worth noting that if you look at the solutions, it will show something totally different, which is fine. So along y equals -1, I'm going to plug in -1 to my function. So I'm going to get f of x comma -1 equal to x squared plus 1 minus 2x plus 4. And the partial derivative of that is going to be 2x minus 2, set that equal to 0. You get x equal to 1. So along the wall, y equal to -1, x equal to 1 is going to be a place where we might have a maximum or minimum. F of. And then along the wall, x equal to 2, we'll do the same thing. We're going to take our function. We're going to plug in 2 for x. So f of 2 comma y And that's going to equal 2 squared plus y squared minus 2 times 2 plus 4. And then the partial derivative of that with respect to y is 2y. Set that equal to 0, and we get y equal to 0. So we also get the point x is 2, y is 0. Right there. Lastly, we look at the wall y equal to x. So I'm going to have f of x comma x, which will be x squared plus x squared minus 2x plus 4. Welcome. Thanks. Working on this. Well, you might notice I've actually used the wrong function to start off with, but it's okay. We're on part B. So this is equal to 2x squared minus 2x plus 4. If I take the partial derivative, I get 4x minus 2 equal to 0. So I end up getting x equal to 2/4, which is 1/2. Y is equal to x, so I also get y equal to 1/2. So I get the point 1/2 comma 1/2. You don't have to mark these on the thing. I just like to because it seems nice. So these are the 7 potential points where we might have an absolute maximum or an absolute minimum. And to see which one is which, we have to plug them into the original function. So plugging in 1, 0, I get 1 plus 0 minus 2 plus 4. 1, 1, negative 1, 3. Plugging in 2, 2, we get 4 plus 4 minus 4 plus 4. So that's going to be 8. Plugging in 2, negative 1, we get 4. Plus 1 is 5. Minus 4 is 1. Plus 4 is 5. Negative 1, negative 1. 1 plus 1 plus 2 plus 4 is 8. 1, negative 1. 1 plus 1 minus 2 plus 4 is going to be 4. 2, 0. 4 plus 0 minus 4 plus 4. And finally, the hard one, 1/2, 1/2. Okay, so we're going to get 1/4 plus 1/4 minus 1 plus 4. That's going to be 1/2 minus 1 is negative 1/2 plus 4 is 3.5. All right, so it looks like there's our minimum and there are our maxima. So we have an absolute minimum at xy equal to 1, 0 with a value of 3. And we have an absolute maxima plural at both 2, 2 and negative 1, negative 1 with a value of 8. There is a third part to this question, but I don't feel like we ever talked about anything like this, nor did he in class. So the third part is to find the absolute extrema over the circular region, x squared plus y squared less than or equal to 1. We can do that if you all want to, but I don't think that that's something we've ever really talked about. And it's probably not the best use of our time. Also, I think it'll probably be more confusing than illuminating, I would think. So if you see something like that on a practice test, let me know. We can talk about it. Like I can make a video and like, post it, or we can come to drop it or whatever. But I'm going to skip that part for now. Well, let's look at part D. So part D, we want to integrate the function f of xy equal to x squared plus y squared minus 2x plus 4 over the region in part B. So over that region there. Okay, so you can do it either way using vertical or horizontal cross sections. My default is to use vertical because that's just kind of normal, but I'm going to do it both ways. So here's our region. If I'm using a vertical cross section, okay, my inner integral is going to be from y equals the bottom to y equals the top. So y equals 0 to y equals x. And then my outer limits of integration are how far left and how far right this thing can go. So a left value of -1, a right value of +2. And then we put the function in here, x squared plus y squared minus 2x plus 4. And then it would be dy dx. Or if you wanted to use horizontal cross sections, you could do that as well. Then the inner limits of integration would be, instead of from bottom to top, from left to right. So a left limit of x equal to y, a right limit of x equal to 2. And then this thing could go as low as y equal to -1, as high as y equal to 2. Same function. And then it's dx, dy. These look pretty similar, right? I mean, there's not a lot of difference here because of the nature of the triangle and the fact that one of the boundaries is the line y equals x. So there's a lot of symmetry here, and that's okay. We can do this either way. It doesn't really matter which way you do it. Let's do it this way. So doing the inner integral, I'm anti-differentiating with respect to y. So I'm going to get x squared times y minus y cubed over 3 minus 2x times y plus 4y from y equals 0 to y equals x. And I'm just plugging in x for every y. So I'm going to get x squared times x minus x cubed over 3 minus 2x times x plus 4x. You could simplify this a little bit, right? The only real simplification you can actually do here is putting these together to get 2x cubed over 3. That's really the only simplification we can make. Is it worth doing? Yeah, sure. So let's integrate this now. So the integral of 2x cubed over 3 is 2x to the 4th over 3 times 4. Minus the integral of 2x squared is 2x cubed over 3. The integral of 4x is 4x squared over 2, which is just 2x squared. -1 to 2. We can cancel a 2 here and a 2 here. So plugging in, we end up getting, let's plugging into 2 to the 4th is 16 over 6, minus 2 times 2 cubed is also 16 over 3, plus 2 times 2 squared is 8, minus, plugging in -1, I get 1/6. -1 cubed is -1, so 2 times -1 is -2, minus -2 is plus 2/3, and then plus 2. And if I were taking a test, I would stop this problem here and go on to other work. And then if I have time at the end, come back and finish this off. Or maybe don't, right? I mean, like leaving it here is a pretty safe bet. I don't know what he wants as far as how much simplification. If I were going to simplify this, here's what I would do. I would say, I would look at the things. Now, I know I can reduce this to 8/3, but I think I'd rather say 16/6 minus 1/6 is 15/6. I feel like that's a better way to take care of that. So I'm going to write this as, so that and that gives me 15/6. Okay, I've dealt with that and that. I'm not really canceling them, but it's how I'm keeping track of what I've done. -16/3 minus 2/3 is -18/3. That's going to work out nicely. And then 8 minus 2 is 6. So simplifying here, 15/6 reduces to 5/2. 18/3 is -6. Oh, this worked out beautifully. I got lucky, right? I definitely didn't know that was going to happen when I chose to put that with that, but it worked out. What's up, Parjat? By making an error. Thanks. No, you're totally right. I definitely, yeah. I definitely should have plus, darn. Okay, so I should have a plus there. It's okay, it's not too bad. That should be a plus. That should be a, so instead of having 2x cubed over 3, I should actually have had 4x cubed over 3, right? Because x cubed plus 1/3 x cubed is 4x cubed over 3. It's going to be a 4x cubed over 3. So instead of having 2x to the 4th over 3 times 4, I should have 4x to the 4th. Which means I should be able to cancel out a 4 and a 12, 4 and a 4, and leave me with a 3 instead of a 6. Okay, so I really should have, let's see, so I plug into 16/3 minus 16/3 plus 8. Well, great, those just cancel each other out. And then I have a, plugging in the -1, I'm going to have a 1/3 plus 2/3 plus 2. So simplifying this, I really have 8 minus 3. Just, sorry. It's going to equal 8 minus 1 plus 2 is 3. So the answer is actually 5. Good eye there. Sorry, I missed that earlier. Other questions or observations about this one? I assume your test is cumulative, right? Because of course it's cumulative. Why wouldn't it be? All right, let's look at the next one. Find the linearization of f of xy equal to x squared plus xy cubed at the point 2, 1, and then use it to approximate f of 2.02, comma 0.97. Sorry, that looks terrible. Okay, so I'm sorry, I don't want to see the things. So the way I remember the formula for the linearization is the following. The linearization is equal to your function evaluated at your nice point plus your partial derivative evaluated at your nice point times x minus your nice x coordinate plus your partial derivative with respect to y evaluated at your nice point times y minus your nice y value. It's extremely similar to the linearization formula as a function of one variable, just an extra piece. So let's see what we've got. Let's see, f of 2, 1 is 4 plus 2 times 1, which is 6. fx is 2x plus y cubed. So fx evaluated at 2, 1 is 4 plus 1. fy is 3xy squared. If we plug in the point 2, 1, we get 3 times 2 times 1, which is 6. So then throwing all of this into my formula, my linearization of xy, of the function, I should say, is f of 2, 1, so 6, plus fx, 5 times x minus 2, plus fy, 6 times y minus 1. And I would leave it like this. You certainly could simplify it and get L of xy as 5x plus 6y plus 6 minus 10 minus 6. That would also be fine. But if we're going to plug in these points here, I think it's going to be really challenging to do 6 times 0.97. Right? That seems like a lot of work. It's going to be much easier to do 6 times 0.97 minus 1. That's going to be an easier thing to do. So make your life simple. Use this unsimplified version of the linearization to calculate the approximation. So then we can say, all right, f of 2.02 comma 0.97. The whole point of this is that the linearization approximates the function near the value. So we're plugging in 2.2 comma 0.97 into our linearization. And we're going to get 6 plus 5 times 2.02 minus 2 plus 6 times 0.97 minus 1. That's going to be 6 plus 5 times 0.02 plus 6 times negative 0.03. So that's going to be 6 plus 0.1 minus 0.18. So that's going to be 6.1 minus 0.18 is 5.92. Not too awful. I'm curious. So in case you're curious, if you actually plugged in those numbers to the original function, 2.02 squared plus 2.02 times 0.97 cubed gives us 5.923999. So pretty good approximation. I mean, as we typically expect. If you're doing linearization at a point that's not too far from the original point, it's usually a pretty decent approximation. What the heck just happened there? Okay, fine. Be that way, Zoom. Share my screen again. What is going? That's weird. I think the app just closed for it. Okay, all right. Be that way. We need to update this app, I think. Okay, share my screen. Sorry about that. Technical difficulties. All right, move along. So number 3. Consider the function f of xy equal to the square root of 25 minus x squared minus y squared. I want you all to find the domain. Give you a minute and a half. And sketch it too. If you found it, sketch it. Should be getting a familiar shape. So to find the domain, we're going to set the inside of the root to be greater than or equal to 0, like we usually do. And then whenever I'm doing a domain thing, if I see it like x squared plus y squared or negative x squared minus y squared, I know I always want to kind of isolate that. So I really want x squared plus y squared by itself. So I'm just going to add x squared plus y squared to both sides. So I'm going to have that 25 is bigger than or equal to x squared plus y squared. Or as I would probably imagine it in my head, x squared plus y squared is less than or equal to 25. If I'm thinking about drawing this, I'm thinking about graphing it when there's an equality. So I'm going to graph x squared plus y squared equal to 25. which is the circle, center is the origin, radius is 5. And then we always have to ask ourselves, do we want the inside parts or the outside parts? So we test a point. If you test the origin, 0 plus 0 is definitely less than 25. So the origin is in there, which means everything on this side of the boundary is in there. So this is my domain. If I was going to describe it as a set, I would say that the domain is the set containing all points x and y, such that x squared plus y squared is less than or equal to 25. It always feels kind of weird to write the domain because we've already essentially written it that way. We just have to be more specific about it. I feel like there's something else I want to say about this. Maybe not. Yeah, that's more of a 21C thing, I guess. There are things I want to say about this in a different class, not this class. Range. Just thinking about the output values. Okay. So when you think of range, you should really just ask yourself, okay, how big can the function get? Well, if I'm doing that, I find it really helpful to rewrite it just a little bit as the square root of 25 minus parentheses x squared plus y squared. So to make this thing big, I need to make the inside as big as possible. To make the inside as big as possible, I have to subtract off as little as possible. So what's the least I can subtract off? What's the least x squared plus y squared can ever be? That's the biggest it could be in this case. So what's the smallest x squared plus y squared? Just x squared plus y squared. At the very smallest, x squared plus y squared could be right, 0. That's why we always look for the x squared plus y squared, because there's always this, I don't want to say artificial, that's not right. There's always this restriction that x squared plus y squared has to be non-negative. There is no way to make it negative. So if x squared plus y squared is greater than or equal to 0, then we know that the smallest this whole thing can be here is 0. And so the biggest this thing can be is the square root of 25 minus 0, which is 5. That's the biggest it can be. How small can it be? Well, in the same sort of way, if we make this entire thing big by making the thing we're subtracting off as small as possible, then the way we make it small is by making the thing we're subtracting off as large as possible. And we already know how large it can be. That's part of our domain restriction. The largest x squared plus y squared can be is 25. So the smallest this whole function can be is the square root of 25 minus 25. So our range here is bracket 0 to bracket 5. You can draw some level curves. Level curves for z equal to 3, 4, and 5. So here's what you don't want to do. You don't want to take your function and set it equal to 3, and then 4, and then 5, and bracket 20. What we want to do is set our function equal to c. And then we will plug in the different values once it's easier to see what's going on. Well, kind of like when we were finding domain, I want to isolate x squared plus y squared. So I'm going to square both sides. And then isolate x squared plus y squared. So I might have negative x squared minus y squared equal to negative 25 plus c squared. And then multiply both sides by negative 1 to get x squared plus y squared equal to 25 minus c squared. So here's what I know about this. This is a circle. Center is the origin. And the radius is the square root of this number over here. Right, this is much easier than plugging in 3 and doing all the work, and then plugging in 4 and doing all the work, and then plugging in 5 and doing all the work. Instead, I can see that when z equals 3, I'm going to get a circle of radius 25 minus 9. Square root of that is going to be the square root of 16, which is 4. When z equals 4, my radius is going to be the square root of 25 minus 16, which is 3. And when z equals 5, it's kind of unexciting, but my radius is going to be square root of 25 minus 25, which is 0. It just makes it easier to graph it all at once instead of kind of doing it bit by bit. So I'm going to graph my level curves. My radius is 0. It's kind of boring. It's just this point here. So that's my level curve when z equals 5. And then when z equals 4, my radius is 3. So pretty good. Here's my level curve when z equals 4. And then my radius is 4 when z equals 3. So I go down 1. Got too confident. Oh well. There's my level curve when z equals 4. Sorry, z equals 3. Apologies. So we can see that at the highest, when z equals 5, you've got this little point. And then if you go down, you get wider circles and wider circles. And in fact, we could even do one more just for fun. If z equals 0, we get a circle with a radius of 5. So down here at the very bottom, when the lowest level, 0. Sorry. Killing it in a bad way. At the very bottom, you have a circle of radius 5. You can imagine what we have as a hemisphere, right? At the top, you have a point, and then you just get wider and wider circles until the bottom, we have a circle of radius 5. So we could draw the 3-dimensional shape. And we meaning not me, really. Try, I guess. Then that's not too terrible, I guess. He says before finishing the picture and making it terrible. There's our hemisphere. Beautiful. Okay, a couple more questions to do with this. So still, kind of used up all my space here. So we want to plot the point 3, 0 on the correct contour in our level curve graph. Okay, well, if I plug in 3, 0 to my function, remember my function is the square root of 25 minus x squared minus y squared. If I plug in 3, 0, I get the square root of 25 minus 9 minus 0, which is equal to 4. So that means the point 3, 0 should be on the level curve when z is equal to 4. So that should be x is 3, y is 0, and the z value is 4. So there's the point right there. And then the next question is, based on your plot, is z increasing or decreasing in the x direction at 3, 0? It's a good question. So if I move in the x direction, so when I move in the x direction, what direction do I mean? I mean up, down, left, or right? Well, I know what it's not. I know it's not up or down. But is it left or right? It's a fair question. So when we say we move in the x direction, what is implied, although not always explicitly said, is that you're moving in the positive x direction. So you're moving to the right. So if I move in the positive x direction, are the z values getting bigger or smaller? And I know it would be nice if my graph was a little easier to read. This line here is the z equals 3 line. This line here is the z equals 0 line. Here's equals 4, here's equals 5. So as I move from here to the right, Z values are getting smaller, which means that's right. So let's not try and write everything on the same page, James. So as we move in the positive x direction, the Z values get smaller. So what this means is that we expect the partial derivative with respect to x at this point to be negative. Right? If the function is getting smaller in a certain direction, you expect the derivative in that direction to be negative because the function is decreasing. What about in the y direction? So as we move in the positive y direction, and this question is not going to have as nice an answer as you maybe want it to. So if I start here and move upwards, well, in general, it looks like the things are going to be decreasing, right? My Z value, I'm starting at the Z value of 4 and I'm moving towards the Z value of 3. But what's probably going to actually be the case here is since the direction of motion is tangent to the level curve, it probably means we're going to have a derivative that's equal to 0 actually. So as we move in the y direction, I also think the Z values get smaller, but we will probably get that the partial derivative in the y direction is actually equal to 0 because the direction of travel is exactly tangent to the level curve. Let's check it out and see. So here's our function, f of xy equal to, I'm going to write it as 25 minus x squared minus y squared to the 1/2 power. If I take the partial derivative with respect to x, it's 1/2 times my stuff to the negative 1/2 times the derivative of the stuff, which is negative 2x, versus fy is the same sort of deal, except it's going to be multiplied by negative 2y. I was a little worried for a second. I thought, oh, maybe I'm wrong about this 0 thing, but I'm not. I thought it might be though. So if I plug in my point, fx at 3, 0 is going to be 1/2 times 25 minus 9 minus 0 is 16 to the negative 1/2 power times negative 2 times 3, which ends up being, I don't know, 16 to the negative 1/2 is 1/4. So you get negative 6 over 8, which is negative 3/4. So definitely if you move in the x direction, the derivative is negative, we're decreasing. On the other hand, if we move in the y direction, that's a y. Well, I'm not going to do all the work because I can see that when I plug in 0 for y, that part's going to be 0. So we're definitely going to get 0. You could probably convincingly argue that it's still decreasing in that direction, but at that particular point, it's a point of tangency, so it's not decreasing. Do you guys ever talk about Bayes' formula in class?
Yes.
Do an example of that. We never talked about it in here. Let's do the last question on this handout. A blood test for disease that affects, so let's write down, so as we go here, a blood test for disease, so we have a disease and it affects 1 in 500 people. So right now, and so let's say D is the disease. The probability that a randomly selected person has the disease is 1 in 500, or 0.002 if you prefer. I don't prefer, but you might. Okay. So the test shows a positive result in 97% of cases when the person actually has the disease. So the probability of a positive test, given that the person has the disease, is 0.97. Great. And then we also know that in 5% of the cases when the person does not have the disease, they also test positive. So 5% of the time, a person who does not have the disease will test positive, also known as a false positive. So the way I would write that is the probability of a positive test given that they do not have the disease is 0.05. Right? The D complement there, the complement meaning the people that don't have the disease. All right. So suppose a random person is tested. What is the probability of having a positive test result? So for questions like this, I think it is most effective to use a tree diagram. So here's what I mean. We have choices. So in the beginning, you select a random person, one of two things can happen. They can either have the disease or not, right? That's kind of it though. Yeah. So they either have the disease or they do not have the disease. And we know the probabilities of both of those things. The probability of having the disease is 1 out of 500. The probability of not having it is everything else, 499 out of 500. One nice feature of a tree diagram is that every branch level has to add up to 100% or a probability of 1. So if that's up to 1, great, I can move on. I suppose also I should mention, I need to start with the disease and not with the test because my conditional probabilities that were told to me are conditional based on knowing the disease. We know the probability of a positive test. So I know that the disease branch has to kind of come first, and then the testing branch has to come second. So now, for each of these cases, whether you have the disease or not, we're going to take a test. And that test could either be positive or negative. We know that if you have the disease, the probability of a positive test is 0.97. Which means the probability of a negative test has to be what? Somebody? Yeah, right, 3%. On the other hand, we know that the probability of having a positive test given someone doesn't have the disease is 0.05. So there's a 5% chance of having a false positive test, meaning there's a 95% chance of having a negative test given you don't have the disease. So if I want to find the probability of having a positive test result, I'm just looking for all the ways I can get to a positive test result. So the probability of a positive test result is going to be all the paths to get me there. So one path is having the disease and having a positive test. So 1 out of 500 times 0.97 plus not having the disease and having a positive test. So 499 out of 500 times 0.05. Instead of doing the math, let me just look at the answers. So about 0.05184. Okay, but that's not the most interesting part. Secondly, we might ask, what's the probability of having a disease given that you have a positive test? And this is the typical sort of situation, right? We want to know, we know that if I have the disease, the probability of a positive test is 97%, but I really am more interested in knowing, right? I'm taking a test because I don't know if I have this disease. So I want to know if I have a positive test, what is the probability of actually having the disease? So the way we're going to calculate this is it's the probability that you have both the disease and a positive test divided by the probability of having a positive test. The way I kind of think about this is in a Venn diagram sort of way. If these are all the people that have the disease, and these are all the people that have a positive test, here's the people that have both. So if I'm trying to find the probability of having the disease, given that you have a positive test, you're taking this whole positive test, that's kind of your new entire sample space. You say, okay, out of all those people that test positive, what proportion of them have the disease? Well, it's exactly this. It's the probability of having the disease and a positive test divided by the probability of having a positive test. You could write out a big long formula for this. I don't necessarily recommend it, but I will write it out. What I'm first going to do is I'm actually just going to calculate it by looking at my tree diagram. So the probability of having the disease and a positive test is this path here, disease and positive test. That's going to be 1 out of 500 times 0.97 divided by the thing we already calculated in the first part, the ways you can have a positive test. This ends up being approximately 0.0374. I will tell you in general, although I don't really recommend memorizing it, you can. This can be written as the probability of having a positive test given that you have the disease times the probability of having the disease divided by the same sort of thing on the bottom. Probability that you have a positive test given that you have the disease times the probability of having the disease plus the probability of having a positive test given that you don't have the disease times the probability that you don't have the disease. Sorry, now it's a very, very we're looking there. That's it's dicey, James. And that is Bayes' formula or Bayes' rule. People call it different things. And the main point of it, to which I stopped, is that if you're given one conditional probability, you can find the reverse conditional probability. And interestingly, right, the probabilities are usually very different. The probability of having a positive test, knowing that you have the disease, is 97%. Whereas the probability of having the disease, given that you had a positive test, is only 3.74%. It's a very, very different. This probability is based a lot more on how prevalent the disease is versus how accurate the test is. This number is usually much closer to how just widely distributed the disease is. All right, that is all I've got. Solutions to this are on Canvas if you want to look at them. I do encourage you to look at them. I think they're good problems. I've enjoyed having you this quarter. Good luck on your finals. I will be in drop-in right now. I'll be in drop-in tomorrow. I'll be in drop-in on Friday. So if you're looking for more help, resources, whatever, I'm available. Drop in the library. I hope your test goes well and hope you enjoy whatever you do during the summer, whether it's more school or taking a break or whatever. Enjoy it. Welcome. Make sure you fill out the attendance form. You're welcome.